Welcome to Unbox, where we unbox open source software. Part 1 was an introduction to Postgres-XL, a high-level overview. Now we'll talk about the core components and what this database really is about. Talk a little bit about what we're going to cover in this video and what you will expect to learn. Alright, so the first thing what we'll do is we'll do a quick recap of the first video, that the things that we discussed, and that was mainly an introduction to Postgres-XL. So if you haven't seen that video, you could probably click on the link below and watch that video. Now we'll quickly recap what we learned in the previous video first. We'll talk about in general from a very high level what are the good points and the bad points of Postgres-XL as an application. Then we'll talk about transactions, all right, because this is an RDBMS database which is a distributed database, so transactions play a very important role, and this is in fact the selling point and why you'll want to use this database. So we'll go into detail of transactions, so we'll talk a lot in detail about transactions. Then what we'll do is we'll move on to the different components that make up this database. First, we'll talk about only the core components, the components that you need to get a Postgres-XL cluster going. When you have a good understanding of those, then we'll talk about all the ancillary stuff that you probably don't need, but you should be putting in place if you want to have a stable setup. Okay, so quick recap of what we did last time around. First, we discussed what kind of tables you can save on this database. So there were two kinds of tables. One is a table that you can distribute, which means that if you have 5 nodes, that table will live on all the nodes and your data will get divided in all of them. That's the distributed table. Second one we discussed was a replicated table, which means that your table, a copy of that table will remain on every machine, which means that they will get copied and they will get synchronized. So the first one is a distributed table where you have lots of data, all right, and you want to save this data across multiple machines. And the second type of a table is where you're going to have a lot of requests coming in. So the data size is going to be small. It's going to be something below of 1 GB hopefully, so that you can keep it in one single machine, and you are going to expect a lot of requests. So this is the reason why you want to have multiple nodes serving your request. All right, so those are the two kinds of tables that we discussed about. Now it's a good idea to mix and match both of these. So if you have some tables that you want to be replicated and you want to have some tables that you want as distributed, it's awesome, go ahead. All right, the second thing that we discussed was what kind of workloads can you put on this cluster. The kinds of workloads that you can put, this is a bifurcation of resources. One is a transactional sort of a setup, which means that you are a backend database for a mobile application or a web application or some sort of an application which is making inserts and selects in a real time, which is you're doing CRUD operations on this database. So you can use this. One of the use cases is this. The second use case is where you're dumping a lot of data in the database and then you're using it like a data warehouse. So what we discussed, the main takeaway for this was that you can use it for either of these situations. You should not be mixing both of these. So this is what we discussed mainly in our last video. All right, let's move on to the next section now. What we'll talk about is, on a very high level, we'll talk about what happens with Postgres-XL. Now, when you look at Postgres-XL, what they've essentially done is they've taken Postgres, all right. Postgres is an awesome database. It's a very old database. We discussed about the history in the previous video. And what they've done is they've taken this database, they've said, okay, let's divide this into multiple components. Alright, so they've taken a single database, now they've divided it into different roles. There is some code that they've written separately, so which they've moved out of the core Postgres-XL, and then they've written out or core Postgres, and then they've written that code separately. But a lot of the code comes from Postgres database itself, and in fact the application that you will be running on your machines will also be Postgres, but a modified version of it. Alright, so the good thing of this is that now, because you've divided this into multiple kinds of roles, you can start scaling components individually. So if you feel that a particular type of component needs to be scaled, then you can scale it independently. Now the negative side is that you have a lot of components. So earlier you just had one database that you had to manage. Now you've got multiple components, and then for those components to not fail, you've got other supporting components. So you get the idea. So the first part, it's got a lot of components, which is a good thing, which means that you can scale different components in different ways. But it's got a lot of components, so now you have to deal with all these components, right? So these are the the good side and the bad side. In fact, distributed applications these days, this is the pattern where you want to break down things into smaller chunks so that you can scale them independently. Now this is not a problem that's specific only to Postgres-XL. This is in fact most of distributed systems face this problem. Alright, one of the main talking points and one of the main things when you look at infrastructure for distributed applications is that you want to avoid single points of failure. None of your components of your application should fail, and if they fail, that's fine, but there should be a backup, which means that your nodes can go down, but your service should not go down. This is, if you've even heard of, microservice architecture, and essentially, if you look at distributed systems, one of the main things that you want to do is that, you want to have redundancy. Alright, so let's talk about transactions. Right. Now, transactions basically are a set of rules that are put in place. These are guarantees that are given so that somebody who's going to use the database knows for sure that they can rely on this set of rules. So a transaction basically or a transactional guarantee is, it follows the ACID rules. So an ACID rule, basically it stands for ACID. So A is for atomicity, C is for consistency, I is for isolation, and D is for durability. Let's talk about these one by one, and they're pretty intuitive and easy to understand. Some of these are fairly important, and we'll get into details and depth of what they are. ACID, atomicity. The word atomicity has its base in the word atom. At one point of time, atom was thought to be the most fundamental block of the universe, where it could not be divided further down, and that's where the name comes from, which means that no matter how many SQL statements are part of that transaction, the entire thing has to either run or it has not run, which means that there has to be atomicity as part of it. So that is A, atomicity, which means that even if you have a transaction which is a bunch of 50 SQL statements, all of those will either run or they will not run. That is atomicity. C is consistency. Now, when you create tables, you have different kinds of rules that need to be followed, which means that you may have foreign key references, you may have triggers. All of those rules need to be followed. They need to be, you need to ensure that those rules are covered. That is C, consistency. Third one is the big one, which is isolation. Now, in isolation, what isolation really means is that when the transaction runs, is going to run as if it is the only thing that's running, which means that if the transaction was the only one that was running at that point of time, and how it would behave, that is what isolation essentially means. So if you were to run 50 SQL statements, if all of those were running without anything else running on the database, and how it would behave, that is what isolation essentially means. All right, and the last one is durability, which is that all of your transactions or all of your SQL statements and everything that you've run on the tables, even if your machine shuts down or if your database shuts down, is going to remain. It's not going to go away. So that part is durability. So we spoke about ACID, so ACID. Now A, C and D is fine. Let's talk about isolation, because that's where we're going to come into, and that's where the Postgres-XL part is going to come into context, and where you'll understand why we're talking about all of this. And that's a little tricky to understand also. So if you talk about isolation, and let's take a simple example, and you'll get an idea of where I'm coming from. For example, if you have a users table, all right, and for simplicity's sake, we're going to say that there are 3 transactions that are running at one point of time, and you have transaction A, you have transaction B, and you have transaction C. Now at the start of these 3 transactions, we're going to assume that there is for example 5 or 10 users in the users table. This is a very simple table. Now what we are saying with isolation is that the transaction has to run as if it was the only thing that was running on the database at that point of time. Now, so let's take the context. Say transaction A starts, is going to insert 100 users. Transaction B starts, and this is going to go in and also make an entry of 200 users. And transaction C is going to do inserts, and then is going to also go in and do some sort of updates. All right. Now, if the 3 of these are going to run in parallel, and if the 3 of these have to see the view of the world that it saw when it started, right? The isolation piece also means that when the transaction runs, you've got to see the world as if no other changes had happened. Also, what it means is that to the world, when you are running, the changes that you make to the database should not be seen until your transaction has been committed. Which means that if transaction A starts and it makes 10 inserts, and then it completes the inserts, then it has to commit. The moment that it started and the moment that it committed, in between is going to make the actual writes. For the sake of understanding, as a thought experiment, let's assume that if it takes 30 minutes to make these 10 inserts, it means that while these inserts are physically happening on the database, if somebody actually sees these inserts, they still should not, or nobody should see these inserts until they are actually committed. So that's where the rules of isolation come into play, which means that if some other transactions are working on the database, you should not be able to see those changes until they are committed. And the other thing that we spoke about first was that when you start the transaction, the view of the world that you see right now has to be the view of the world that you see throughout the entire transaction, because we are assuming that it is going to run as if it ran in isolation. In isolation, no other changes are going to happen. So, but obviously we can't have it run in isolation technically, because your database is going to become so slow then. So it's obviously not possible. Alright, so with these 2 rules in mind, which is the first rule that if your transaction runs, it has to run as if nothing else in the world is running at that point of time. And the second one is that only once you commit the changes of your transaction will they be visible to the entire world, right? With these 2 simple rules, let's go back to our example and let's talk about the transaction A, B and C. All right. Now transaction A, let's say, makes 10 inserts. Transaction B makes 20 inserts, and transaction C is going to go in and do a bunch of changes that may be inserts and updates together. They are going to take varying amounts of time. The first one, let's assume, is going to take 1 minute. The transaction B is going to take, let's say, 5 minutes, and transaction C is going to take 15 minutes. Right? Now, when transaction A commits, okay, even though the changes have been committed, transaction B, while it is working, still should not be able to see the changes that transaction A did. The reason is because inside a transaction, everything has to work as if there were no changes to the database that happened, right? So to technically achieve this, okay, on the database level, this is what actually happens. Whenever a transaction starts, it goes out and gets itself a transaction ID. Now obviously it's more complicated and this is oversimplified, but you can think of a transaction ID as a single numerical number that increments, right? So for example, if I am transaction A, I will go out and get a transaction ID. It may be transaction ID number 5. If let's say I'm transaction B, I will also go out and get myself a transaction ID, which may be let's say transaction ID number 10, and C will also get a transaction ID, which may be transaction ID number 15. Okay, these are arbitrary numbers, just for the sake of this example. The way it will technically work is that while a transaction works, it goes out and whenever it tries to make some changes, right, it keeps a track of the transaction ID, and on the record level, on each and every record, there is a reference as to what transaction inserted this record and what transaction updated this record and what transaction deleted this record. Okay, so when you now when any transaction is dealing with records, what it does is it looks at the record and technically it can see all the records that are written because they are all written to disk, and the transaction can view all the records that are there. But to be able to give you the transactional guarantees, what it does is that essentially it will look at its own transaction ID, and if it encounters a record which got inserted by a transaction which was higher than its own transaction ID, which means that it got inserted after the transaction which is itself it started, which means that this is a record from the future that it cannot see this record, right? Now if for example, let's say a record has been updated by a transaction which is in the future, right, it is updated by a transaction which is higher than its own transaction ID, it will disregard that as well because it should not be able to see things in the future, right? This is how updates, if a transaction or if a record has been deleted, it's going to work in the exact same way. So now you can guarantee saying that any of the records that are inserted after the transaction has started will not be updated, inserted or accounted for by this transaction. So essentially what you have is you have a snapshot view of the world. Whenever your transaction started, you have a snapshot of the entire database and all the tables that are there as part of it, where you have a transaction reference. So this is how isolation is maintained on the table level when the transactions happen. Any transaction that runs on the database, or any SQL statement that runs on the database, even though you're just running one SQL statement, is actually a transaction. So it works with the transactional guarantees on Postgres, right? So now the reason why we're talking so much about transactions is that once you understand what transactions are, then you will understand the roles of the components and why they're created, and if something is not working, why it's not working. Alright, so what we've learned with this, or if you've if you want to take one thing away from this, is that transactions are very important to a relational database, and anything that it does and everything that it does works with transaction IDs. And if a SQL statement going in and wanting to run on the database, or if a transaction wanting to run on the database, a bunch of SQL statements wanting to run on the database does not have a transaction ID, it does not have a context of the view of the database, and so it cannot run. Alright, so this is some background about what transactions are and why they are important to relational databases. What we'll do next is we'll go into the core components of Postgres-XL, and we'll talk about what their roles are, what they do, and once we've covered those, we'll move into the ancillary stuff. Now the ancillary stuff we'll not cover as part of this video because it's going to get really long, so we'll take that up as part 3. So in this video we'll cover the core components and the things that you really need to get a Postgres-XL cluster going. Alright, so let's go to the next section. Okay, so we discussed about transactions and how important they are. Now what I've got in front of me are the main 3 components that you will need to get a Postgres-XL cluster working. Okay, if you have these, then you can have a Postgres-XL cluster. You will need more components to work with when you have a setup done in production, so that you have failovers set up. But let's talk about the individual components, and we'll go into the specifics of how they interact with each other and what they do. All right, I like to think about the internal components of distributed systems, or even otherwise, in terms of physical stuff that I can feel, because it helps me reason out how they interact with each other and what they would do in a certain situation. So that what I feel is, if you understand this as a fundamental concept of how the system works internally, and a lot of times these systems are not very complex, they are not very complicated. If you can understand the internal parts and how they interact with each other, then you can really reason about what's going on with the system, where you need to troubleshoot, and how you can get something up and going. Right? Otherwise, these systems can tend to be very complex, and with so many moving parts, you won't even know where to begin your troubleshooting if something goes wrong. All right, so let's start with the 3 components. These are the 3 main components of the system. Now these 3 components are, this is your GTM, then you've got your coordinator and your data node. All right, so out of these 3, 2 of these components are actually Postgres installations, which means that you have a Postgres server running. It's modified code. It's not actually Postgres, but you have a certain version of Postgres running on your machine. So you've got your coordinator, which is a Postgres instance, and a data node, which is a Postgres instance. Now in this component can be scaled, which means that you can scale your coordinators, you can scale your data nodes. And you've got this component here, which is GTM. GTM is basically a custom component that has been written. Okay, we saw how transactions are so important for a relational database, and especially for Postgres. Now you may not want transactions, or it may not be very important for you that when you use this database you don't want the transactional capabilities. But believe me, this database or even Postgres will not work without transactions. It's very important for it. Okay, in fact, anything and everything that it does with transactions. So with that being said, we've got the GTM. Now GTM is your global transaction manager. So a global transaction manager essentially means that it tracks all the transactions of your entire cluster in a single place. Right? Now we saw how important it is for this database to maintain transactions. Now every time there is a request that comes in, it needs to get some sort of a transaction ID. Where is it going to get this transaction ID? And that transaction ID has to be unique across the cluster. It has to be unique across the different nodes that request it. Now, this is the reason why your GTM becomes very, very important. So everybody tries to go out and get a transaction ID. Everybody tries to go out and get a transaction ID from the GTM. So the coordinator will go to the GTM, ask for a transaction ID. The data node will go out to the GTM, ask for a transaction ID. So any interaction that happens on the database has to happen in relation to a certain transaction, because we saw that you could have multiple transactions running. You can have some transactions that are started, other transactions that are not yet committed, which means that some of the transactions will not be able to see other transactions because they've been committed after this particular transaction was started. So there's a lot of nuances that the database needs to maintain internally, and to do that it needs transaction IDs. So that is the reason why GTM plays the central role in this database. When you look at the actual application, it's not a very large application. It's again written in C. What they've done is they've taken certain portions of the code of Postgres and they've separated it out, and that makes your GTM, which is your global transaction manager. They've taken that application out. It's a small transaction, and in fact it needs very little resources to run. So if you have a relatively small machine, if you give it maybe 2 to 4 cores, and if you give it 4 GB, it's going to run happily. It's not going to need too many resources. In fact, even in terms of your data footprint, it doesn't need too much. It doesn't write too much. It just writes its own logs, and it just tracks what transaction ID is going on, and what are the members that are there in the cluster at this point of time. So it doesn't do too much, but whatever it does is very important, and if it stops doing that, then you're in for some trouble. When you talk about helicopters, there's this thing called the God nut, right, or the Jesus nut. Why they call it the Jesus nut? Because that's the nut that sits between the blades of the helicopter and the body of the helicopter, right? That's the main nut that connects both of these portions. And why it's called a Jesus nut is because if that nut has some failure, then praying to Jesus is the only thing you can do. Okay, so in terms of this database, this guy is your Jesus nut, right? GTM goes down, you're in for some trouble. Most of your stuff will not work. Okay, so GTM is a small application. It's got a small footprint. You cannot scale this. You cannot have multiple instances of the GTM working. It is a single point of failure, which means that if it fails, then everything is going to stop. Okay, you can have backups for it. You can have backup strategies, fallback strategies for it in case it goes down, but it is an important and a core component of this database. So this is the GTM. There are some limitations also in this. These are explicit limitations because this application is written in C and it's written in a certain fashion. There is a particular limitation in this application where it can only accept 1024 connections at any point of time. So if you're going to have really high throughput coming through, and if you're going to have a lot of requests, then only a single GTM is not going to be able to handle all of those requests. In a little while we'll talk about how we can mitigate this. So there is a solution for this as well, right? But this is something to keep in mind. You can have only one of them GTMs. It cannot die, right? There is a limitation. So if you're going to have high throughput transactions, so if you're not going to have, let's say 5 or 10 users use your cluster, and just run really heavy reports. If you're doing that, then I don't think you're going to put too much pressure on the GTM, so you can be fine directly just using the GTM and you're not going to face this issue. But if you excuse me, if you have a lot of requests coming in into your coordinator and you're serving a lot of requests, then you can't go with just the default connection from the coordinator to the GTM and from the data node to the GTM. It's going to cause some problems. Okay, so we'll talk about the components that will help you to solve this problem, and that's the reason why those were created. But this is the story of the GTM. Very important part of the application. Okay, need to be, most of the times you need to be sure that the GTM is working fine, and a lot of times what you'll see is if components of your database can't connect to the GTM, or if your database starts to fail, most often it is probably because your GTM has gone down. So if you restart your GTM, then your other components will just start working on their own. So that's your GTM, that's the first thing. Then we'll move on to the other two main components. These other two main components are your coordinator and your data node. So first let's talk about the coordinator. Now the way the coordinator is made is that this application does not save any data. This particular component does not save any data within itself. It's like a project manager. So if you take an example, if you take the example of a team and how a team is managed. So you have 4 or 5 team members, and then you have one project manager or a technical project manager. So this person is responsible for, let's say, taking the requirements from other people, figuring out what needs to be done, how it can be done, and then going out and distributing that work to the team members and telling them what needs to be done. The team members complete the work, give it back to the project manager, and then the project manager then returns back whatever work to the end user, to the client, and then that's how it works. So this is an example of how you can think about a coordinator. The job of a coordinator is essentially to be the face of your cluster. So all the requests that you will receive, they will come to the coordinator. Now the coordinator does not have any special protocol. You don't need any special drivers to connect to it. Anything that can connect to a Postgres database can connect to this, right? So a coordinator is a Postgres instance. You can think of it as a single Postgres instance. So for example, if your reporting system can connect to Postgres, then you can give it the IP address of one of your coordinators or multiple coordinators, and the requests can go in here, they will get fulfilled, and then you will get the answers back. So the job of the coordinator is that it will accept queries coming in from outside. It will be the face of the cluster, and it will decide where these queries need to get run. It will hand over these queries out to the data nodes, and the data nodes will return back the results to the coordinator. The coordinator is then going to go back and give the results out. So nobody talks to data nodes. Everybody talks to coordinators. Coordinators themselves don't save any data. So even if you put in an insert request to the coordinator will not save this data. It will figure out where this data needs to get saved, and then it saves it to the data node. Now, before we move into the specifics of what they do, let's remember again, there are two kinds of tables. One is tables that are distributed by hash, and the second kind of tables which are replicated tables. So first we'll talk about distributed tables, where data lives where the data is divided across multiple nodes and it lives in multiple data nodes. We'll talk about that first, and then we'll talk about replicated ones because those are simpler. All right. Now, in a distributed table, the data lives across multiple data nodes. Now, this becomes important where if an insert query comes in into the coordinator needs to figure out where this data is supposed to live, in which data node this data is supposed to live. So if you step back and if you look at data nodes, when you log in into one of these, you will see that you are able to query and you're able to see all the tables that you've created. You're able to see all the databases that you've created, and assuming that you only have distributed tables in your database, you will be able to see all the tables. But when you log in into the data nodes, you will only be able to see the data that actually lives on that particular data node. So if you have 4 data nodes, for example, and your data is equally distributed amongst all of them, if for example you have 100 records and each data node has 25 records, when you log in into the data node, you will only be able to see the records that it actually holds. So if it has 25 each, when you log into a particular data node, you will only be able to see 25 records on that data node. Remember, when you log in into data nodes, you will only be able to do select queries. You will not be able to do any inserts directly. You will not be able to change any schemas, or you will not be able to change anything from data nodes. All right, now moving on, and how they work with each other. So now we've learned that for distributed tables, the data lives on individual data nodes. All right, and the coordinator does not have any data saved on it. So what happens is that the coordinator figures out where this data lives, and then it goes out and runs the queries on the data nodes. It figures out if it can. All right. Now, the way the data is inserted, before we move on to how the selects happen, we'll first look at how the inserts happen, and then you will be able to understand how it does the selects. This will also give us some clues on what are the right approaches to running queries on your cluster. When you do inserts on a distributed table, what happens is when you create that table, you tell Postgres-XL what your distribution key is, which means that you tell Postgres-XL how you should decide where that particular record needs to live. Okay, so for example, if you have 4 data nodes and your table is divided amongst those 4 data nodes, Postgres-XL needs to be able to decide when you insert a record into that table, where that record will live from those 4 data nodes, where it's supposed to save that record. Now, to make that decision, what it does is it takes the primary key, it takes the distribution key that you've decided, and whatever value for that particular record it gets, it runs a certain algorithm on that. The result of that algorithm is a number. So if you have 4 data nodes, then it will be a number as to where that record needs to go. So for example, if you give it ABC, then it will run an algorithm on it, and in the end it may come up with a result of 3. So that particular record will go into data node number 3. All right, every time it sees ABC, it will always go and give an answer of 3. That's the important part. So we're putting this in very, very simple terms. Obviously it's more complicated, but in a very simple way, if it sees a particular record, it's going to calculate a particular number for it given a certain number of data nodes. So in our case, we said that ABC will equal to 3. So every time a coordinator sees ABC, is going to give an answer of data node number 3. So if I say, okay, insert into this table and the distribution key is ABC, it will then decide that it needs to save this record in data node number 3. Okay, this is a fairly important part of distributed tables because this gives you a clue as to how this application works, and it will also tell you how you can performance tune this application. So we said ABC lives on data node number 3. Let's say we have XYZ. XYZ will then For example, give an answer of data node number 1. So that record that you're trying to insert with a distribution key of XYZ, if it calculates to data node number 1, then that particular record will go into data node number 1. All right. So we've understood how it saves the data. Okay. Let's look at how it queries the data. When you run very simple queries and queries with the where condition which actually has the distribution key. So in our case, in our table, we inserted two records. One was ABC and another was with XYZ as one of the columns and one of the keys. If I run a query and I say select star from my table where my primary key, whatever the column name is, equal to ABC. If the coordinator sees this kind of a query, now it knows that you passed the distribution key. So from the distribution key is going to run the same algorithm, okay, and figure out if it got this query for an insert, where would it have kept this data. So it runs the same algorithm. Now in our case, we said that if it was ABC, it will go to data node number 3. Now in this case, we are trying to do a select. So in a select, if it sees ABC, it knows that ABC should live in data node number 3. In this case, because it knows the distribution key, is going to run a query directly on data node number 3. Data node number 3 will have that record. It will give back the result to the coordinator. The coordinator will give back the result to the user. So this is going to be a very fast query because it knows where your data lives. It goes out to that particular data node. The data node gives back the result and you get the result back. Okay. In a situation where you don't pass the explicit where condition and you say that my distribution key is this, then in that case you may have given another bunch of where conditions. In that situation, your coordinator will not know where to find this record on your cluster, which is also okay. Which means in that case, what it does is it takes the query and it sends the same query to all the data nodes, because it doesn't even know whether it's going to get one record or if it's going to get 5 records or 10 records. Let's say if you don't explicitly give it a limit, even if you do give it a limit, it doesn't know where the data lives. So it needs to go out and query all the data nodes. All of the data nodes will run this query internally on their own database. It will check if it finds any records. If any records are found, it will give back the results to the coordinator. The coordinator will then hand over the results back to the user or whatever calling application requested for it. So this is how the queries are run on this database. So coordinator only does the job of figuring out where to save the data. If it can figure out where the data lives, it will also do that and then run very specific queries. If it can't, then it's going to throw that query to everybody in the cluster. Now, if you have a one-off query or if you have a less number of queries that get thrown to everybody in the cluster, it is okay. But if all of your queries are going to get sent to all the data nodes, then it's going to be very expensive for your data nodes and you're not going to have high throughput, or you're going to have performance issues. So this is how a coordinator saves data into data nodes and how it retrieves or how it tries to retrieve data from data nodes. Data nodes in themselves don't know about or don't directly interface with other data nodes and other coordinators. If a request is sent to the data node, it will process that request and send the data back. So the heavy lifting of the cluster or the heavy lifting of processing or of coordinating the data is done by the coordinator. The actual work of crunching the data, of figuring out or running through all the records is done by the data node. So a data node in terms of resource utilization demands the maximum amount of resources. So when you plan a cluster, a data node is the node where all of your work is going to happen. So it will need a high amount of RAM, it will need a good amount of CPU, and it will need fast drives, because that's where all your writes, where all your reads are going to happen. Okay, you can get away with a lower amount of resources on your coordinators. It's acceptable, it's fine, because you're not going to do too many heavy writes on your coordinator. You're also not going to do too many reads from your hard drive, so you can get away with lower amount of resources on your coordinators. In fact, I've seen certain clusters where you may run your coordinators on virtual machines, but use dedicated machines for your data nodes. All right, so the heavy processing happens here, all the requests get taken in over here, and this is where all the responses come back from also. All right, so these are distributed tables where the data is saved amongst a lot of data nodes. Then moving on to replicated tables. Now in replicated tables, all of your data of a single table is copied to all the nodes. So any of the data nodes where a query is hit will be able to give you the exact same response back as any other node. So there is no particular figuring out where data lives for this particular query. You can the coordinator can decide to use that or run that query on any of the data nodes, and it will get back the same result. So it can basically query from anywhere. So in this case, you don't need to really worry about how you're defining your table, and you don't need to define any primary key that is used for distribution. All right, so the way inserts happen in this is a little different. We'll move on to inserts also. Selects can happen from anywhere, so selects are fairly simple and straightforward. Selects can happen on any of the data nodes, and they will give you back the results. For writes on a replicated table, the way the coordinator handles writes is that there is something known as a preferred data node. So a preferred data node is the data node where the coordinators will prefer to write. So whenever you get a write, it will actually write to that particular data node, and then the way these data nodes interact with each other is the moment a particular data node gets a write request, those will then at the background flow through to the other data nodes. Okay, boys and girls, so that was a long video. All right, we spoke about a lot of things, and we covered a lot of content. We spoke about transactions, how they work, how they are relevant to what we're talking about, how they're relevant to Postgres-XL. We saw the three main components of Postgres-XL and how they interact with each other, what is the role of each component. Also, what we covered after that was how do you do writes and how do you do reads for distributed tables and for replicated tables. So this should give you a fairly good idea on the theory of how this database works and what are the different components and how they interface with each other. Now what we'll do in the next few videos is we'll do a installation of the entire cluster and also some of the ancillary components. So probably we could cover that both of these things as part of one video, where we'll do an installation of a cluster, and then we'll also introduce all the other stuff like GTM proxy, and there's GTM slave. So there's also data node slave, and there's also other components. So we'll talk about these components and we'll also install them. So that's a good idea. What we'll do is we'll set up an entire cluster, and once we've got that set up, we'll also put in the failover components and stuff like that, so you get a feel of what it is like to set this up. All right, so thanks for watching, and if you like it, like and subscribe.